I'll continue with Stein's method. So today we'll talk about Poisson approximation mostly, again with applications to random graphs. Before I do that, I want to talk a little bit about, there was a question yesterday about these Stein operators. How do we come up with them? Are they different ones? And so I want to, I've added some slides this morning to show you a little bit about how you can derive such operators that characterize a specific distribution. Okay, can you tap? Okay. So there's a few approaches. Let me quickly go through a few of them. Most of them, for the normal distribution, for example, will give you the same operator. So the first approach, that's essentially what we've done with the normal distribution, is what's called the density approach. So if you have a distribution with density P, you can just use integration by parts. That's the same calculation. You start with phi prime, you use integration by parts, you put the derivative onto P, and then you write it as expectation again, but of course, it doesn't factorize like in the normal case, so you have to multiply and divide by P and write it down as an expectation again. So that's what's called the density approach. So all this, the standard univariate continuous distributions, you can try this out and get an operator of this form. For the normal distribution, as we've seen yesterday, P prime over P is just minus X, so you get back the regular Stein operator for the normal distribution. The more important one, the more influential one, is what's called Barber's generator method. And that based on the following observation, if you have a ergodic Markov process with the stationary distribution mu, that's the distribution of interest, that's the one you want to approximate with, which has a generator A, then it's a standard result from Markov process theory that if you take A, you apply function to it, you plug in the stationary distribution, you take expectation, you get 0. And usually this is characterizing. That means this is 0 if and for all F, if and only if Z has distribution mu. Of course, you have to be careful. If you have boundary conditions and things like that, you'll end up with having to have more conditions on phi. Maybe if there's a boundary condition, a reflecting boundary, then phi needs to be 0 at that point and things like that. So these are things you have to worry about. For example, you can use this to derive a Stein operator for the exponential distribution. You take a reflected Brownian motion, and with drift to 0, there has a station distribution that's the exponential, and you can derive the one operator that way. I can give you an example. Langevin dynamics, again, that was Dutika, I think, who was talking about that or mentioned that in her talk. That's a diffusion defined this way. So here U is a potential, and you have the gradient coming in here as a drift. And if you calculate, or if you look at the station distribution, it has this form e to the minus ux with some normalizing constant. And so you can do you can figure out the generator of that, and you end up with an operator of this form. And indeed, that will be characterizing this distribution e to the minus ux. You can do that, for example, for if you want to get back the Gaussian distribution, you can take an Ornstein-Uhlenbeck process, and you're going to get back the same operator. But you can do this multivariate as well. So that's the advantage of this. You can use that for multivariate distributions as well. And for example, the multivariate standard Gaussian has this, but you can use this potential here, and you get back this multivariate version of the Stein operator. But this was mostly introduced at the end of the 80s by Andrew Barber in two cases. One is Poisson process approximation, and the corresponding process is what's called an spatial immigration death process. You have points popping up at different places, and then they'll die with rate 1, and so the station distribution of that is a Poisson point process. And you can also use this for Gaussian process approximation. So you approximate the whole process And the corresponding object is an infinite dimension Ornstein-Uhlenbeck process. So you have like a Brownian motion that fluctuates over time. So the whole diffusion becomes a Markov process. Another one that is what's called a distributional fixed point equation. Eleanor, I think, mentioned that yesterday. For example, for the Poisson distribution, you can characterize a Poisson distribution this way. You take a random variable, you size bias it, we'll see the exact definition later on, and then you remove 1. So you look at this, so you take z, size bias, and remove 1, and then you figure out that this is a fixed point equation. So you're looking for a distribution that if you size bias it, subtract 1, you get back the original distribution, and you can find out that the Poisson distribution is the only one that satisfies this fixed point equation, okay? And many distributions have this kind of characterization. If you write this down in terms of expectations, what does it mean? So you have z, so you look at expectation of phi of z, then you size bias it. So that's the equation that we want, right? That's the definition. So you put in the size bias -1, that has the same distribution as z. But now you write out what this is, and taking expectation against the size bias is just taking expectation against the original one with the variable added in front as a factor and divided by its mean. And so that becomes the characterizing operator, because now you can see you have z on both expressions. You can rearrange this and shift by 1 until you get back the characterizing operator for the Poisson distribution, which we will be using later. Of course, you can do this also by direct calculations. But this has been quite a powerful approach as well for more complicated distributions. You remember maybe in the first talk I mentioned, or was it yesterday? I think it was yesterday, where I mentioned the second order differential operator equation with the density uses a Kummer-U special function. That is impossible to work with directly, but it turns out that distribution satisfies a peculiar distributional fixed point equation, and that's sort of how we derived the whole thing. So this is in certain applications quite powerful. In particular in Poisson approximation as well, which we shall see we will use that for a random graph application. So let's go into Stein's method for Poisson approximation, or sometimes called the Chen-Stein method, or sometimes called the Stein-Chen method. And Louis Chen, this is the Chen here, says it should be called Stein's method for Poisson approximation. Trying to be humble, he says that's what it should be called. So we've seen before, if Z is Poisson lambda, that's if and only if the expectation of lambda phi Z plus 1 minus Z phi Z equals to 0 for all, say, bounded phi, and that goes back to Louis Chen in the 70s when he did his PhD in Stanford with Charles Stein. You can, if this looks rather peculiar, what you can do is you can subtract lambda phi of Z on both sides. So add and subtract lambda phi of Z. And what you can see here, you can rewrite this as lambda phi Z plus 1 minus phi Z. So that becomes a difference. Or you can think of this as a differential. And here we have Z minus lambda phi of Z. So this is, you subtract the mean here, and you can think of this as being the variance. Of course, for the Poisson, that's the same. But you can sort of recognize the Gaussian case, right? You have here this, the Gaussian is centered already, so that will be Z phi Z, and here instead of lambda of this difference, you have just phi prime, and the one in front, which is the variance. In here, this case, we have a variance lambda in front of it. So there's some sort of a resemblance with the Gaussian case if you replace derivatives by differences. So the metric that we usually use when we do approximation with integer random variables, it's what's called the total variation distance, defined as just the sum of the point-wise differences over all point probabilities. You can also write it down as a supremum over the expectation of all over all indicator functions of any subset of the integer lattice. So you compare these two quantities, or you can think of this as well. That's sort of a Kantorowicz-Rubinstein result for a specific metric, that this is equivalent to, sorry, this should be the infimum, not the supremum. This should be an infimum over all couplings of W and Z, and you look at the probability that W does not equal to Z. So you're trying to minimize the best this quantity is the probability of the best possible coupling not being the same. So again, this should be an infimum here. So again, we can check the Stein characterization directly, if you will. You start with expectation Z phi of Z. You write out what this is. Then you can see you can kill the K here with that. One K can be killed. You take out the lambda here, and then you shift everything by 1. So you get back the Poisson probabilities, but now you have lambda phi K plus 1 here, and that's that. So that's the direct way of deriving the Stein operator, which is some sort of morally integration by parts, what you're doing. So again, now we have this operator. What we need to do is to set up the Stein equation, the pointwise Stein equation. So for each so I'm giving you a subset. So let me quickly go back. We're using this characterization of the total variation distance, of course, right? Because this is a supremum over functions of this form, our test functions of this form. So now we have to solve this equation for given subset A of the integer numbers. This indicator function is our test function, so we have to solve this. And this has a unique solution with some boundary conditions at 0, and that has been done. And here are the properties. So similar to when we did this with the normal distribution, here we have the same for the Poisson case. Of course, now we have the lambda coming in explicitly. You could do this also for the Gaussian case, in which case sigma, if you use a general variance instead of 1, you'll have similar factors instead, but using the variance then instead of, you have the variance then coming in a similar way. So what we know about phi is that phi is bounded by 1 over square root of lambda, and that the first difference, which we can think of as a derivative, is bounded by essentially by 1 over lambda. And this is what, if you've heard the term Stein factor or magic factor, that comes from here, because this 1 over lambda can be important in applications, helps you improve your approximation, as we shall see later. So these are what's called, usually now we call them just Stein factors, is these kind of factors in front when we analyze the solution to the Stein equation. So what we need to do now is, I'm giving you an integer random variable W with mean lambda. We approximate it again with the Poisson lambda random variable. So the total variation distance is upper bounded by this quantity, okay? A goes over all subset of the integer numbers, or in this case, non-negative numbers, because Z is non-negative. And so this is what we have to evaluate in order to get a total variation bound on the Poisson approximation. So as a first example, let me mention local dependence, which is what we've done yesterday, right? This, the example that I've given you with triangles, it's a case what we call local dependence. And we can do the same approach here, except that it's easier actually. When you do Poisson approximation, things are a bit easier. So here's the setup. We have a family of indicator random variables, and we assume that P alpha is the probability that X alpha equals 1, which is of course also its expectation. We're looking at the sum. That's what we're interested in. Of course, these can be dependent. We're no longer assuming independence. They can be dependent in any way. And lambda, that's how we choose the parameter for the Poisson approximation. It's just the mean. It's just a sum of these P alphas. There is no variance to match, because if we expect a good Poisson approximation, we expect the variance to be the same as the mean. So there's only one parameter that we match, and the best thing you can do is match the mean. Not necessarily the variance, but the mean is the best, is the optimal choice. So here's our dependence structure that we assume. And that's the same as yesterday. For each alpha, choose what we call a neighborhood of dependence. So you choose a subset of indices such that X alpha is dependent on what's inside and ideally independent of all the random variables outside. But the following result, you can allow some dependence on the outside as well. Of course, you have to make sure that whatever is strongly dependent on Xi goes into that set and whatever is weakly dependent goes outside that set. Okay, so there's a choice that you can, that has to be made, and you try to choose this neighborhood of strong dependence in a best possible way. So there will be just 3 quantities that we'll have to evaluate in the following bound, 3 quantities. And one of them doesn't require any calculation. It's just an expression. And here we know everything, right? Alpha is the sum over all indices, and then you sum over all neighbors of alpha, including alpha, and then just multiply the 2 probabilities. So that's just something you can write down. There's no need to evaluate anything. Then you have to calculate this expression, which is, instead of the product, you just calculate the expectation of the product. That's for the strong dependence, because here beta goes through all the neighbors, but you can exclude alpha here. Otherwise, you would have a strong dependence in here. You would just have P alpha in here otherwise, which we don't want. So this is fortunate that we don't have to include alpha here. So that's something you have to evaluate. And then for the weak dependence, you need to understand how whatever's outside of this, whatever depends strongly on X alpha, whatever's outside of that, that's the weak influence, the weak dependence. Given that, you need to evaluate the expectation of X alpha minus P alpha. Of course, if this is independent of that, then that's just 0 because the conditioning doesn't have any effect. So you're measuring the effect of the expectation on what's outside your strong dependence neighborhood. What effect does it have on X alpha? That's what you're measuring here. And importantly, the absolute value is outside of this. Okay? So you hope that if this influence is weak on that this is close to that. So this condition doesn't have much influence. You're close to 0. So these are the 3 terms, and here's the bound. The total variation distance is bounded by B1 plus B2 over lambda. So that's the first magic factor, and then plus B3 over square root of lambda. You can see this one, the lambda here is smaller. If you think of lambda as large, this is a weaker bound. So you have to make sure really that this weak dependence region has a weak influence on your X alpha, because you're dividing only by lambda. Of course, this doesn't make a difference if lambda is fixed. If your target is a fixed Poisson distribution, then these factors are not important. But if you let lambda go to infinity, then this makes a difference. In many cases, you try to find.
Adrian,
yes.
So this also means that you want B3 to be something that you can bound uniformly in the outcome of the stuff that it may depend on outside N alpha. So it has to be uniform in the realization. Right?
There's an expectation here, so you can do some averaging. But it is an absolute value here, so I guess you need to be a little bit more careful. Yes. I mean, most standard examples are chosen such that B3 is just 0. That means you really have independence outside. That'll be the optimal case. So this goes back to a famous paper by Richard Aratia, Larry Goldstein, and I don't know, Gordon, what's his first name? I don't know him first name. From the end of the 80s, and they wrote 2 moments suffice, Poisson approximations, 2 moments suffice. That was the title or something of that sort. And it's astonishing because indeed, the first moment is P alpha, and the second moment, that's a mixed moment, is this one, and that's all you need to know. That's all you need to evaluate. You remember when we do normal approximation, we had to go up to 3rd moments or even 4th moments, much stronger assumptions that we had to make. But here, for Poisson approximation, 2 moments suffice. That's a rather astonishing fact. So let's apply this first for the easiest case, for the sums of independent random variables, where we have xi are independent. Each one of them is Bernoulli pi, and lambda sum of the pi's. That's what's called a Poisson binomial distribution. So B1, you just evaluate that. So that's just pi squared, the sum of the pi squared. B2 and B3 are just 0 because there's no dependence at all. And so you get this upper bound. Total variation distance is bounded by the sum of the probability squared divided by lambda, and you can pull out the maximum here, and then you have lambda divided by lambda, so the lambda cancels, and you can see why the lambda can be important. It cancels here, so that's the upper bound. And again, in contrast to what's written in most textbooks, where it says, like standard textbooks usually say, you can replace a binomial distribution by a Poisson distribution if n is bigger than 5, and p is small, or np is bigger than 5. There's weird conditions, but this goes back to before when this was proven. As you can see, there is no n here. All you need is that the p's are small for a good Poisson approximation. Okay, that's, if you remember anything from my top of my 3 lecture series, please remember this, okay? Poisson approximation for independent indicators is valid if the p's are small, irrespective of what n is. Okay, of course, if n is very small, then lambda will be close to 0, which may not be meaningful, but the Poisson approximation is valid. Okay, it doesn't matter what lambda is, it doesn't matter what n is, what matters is that the p's are small.
So Adrian, why is B2 equal to 0? Because you are Bernoulli 0, 1, right?
Here.
Yeah, so
because you exclude x alpha itself.
Yeah, good.
That was the important,
okay.
That's the key here, that you remove it. Otherwise, if you include it, that's just x alpha times x alpha, which is just x alpha, and you get a p alpha instead of a p alpha squared. That would destroy your bound. So that's why it's important to have that excluded there. Okay, I'll sink it in. The minimum of p is what's important, not n or not lambda. The maximum, yes, sorry, the maximum of p is what's important. Okay, but there may be cases where the maximum of p is not small. I'll give you an example where this bound is too crude here, but this bound here will be giving you something, whereas this bound is too crude. So the lambda can save you. For example, you take pi to be 1 over I. Okay, lambda will be the sum of 1 over I, and that scales like log n. So the lambda in this case diverges. And you evaluate the bound, you get 2 over lambda. The pi square, of course, just becomes the Riemann zeta function evaluated at 2. That gives you some factor divided by log n, and that converges to 0, although the maximum doesn't go to 0. Of course, in this, there is no limit here, just to be aware. When we do Stein's method, there need not be a limit. The lambda diverges. But we're having a valid Poisson approximation. We're approximating by a Poisson distribution that has a parameter that also grows. There is no limit. But the approximation becomes better. Because it's a finite n bound, really. Okay. Okay, so let's apply this to triangles. We've seen that yesterday. We'll apply that Poisson approximation, see what we get. So we have T, that's the number of triangles in G and P. We saw x alpha is just the indicator that alpha is just a triplet, right? A triplet of 3 vertices, and this is just the indicator that that triplet, all 3 edges are present. And so the expectation, the p alpha is just p cubed, all 3 edges have to be present, and lambda is just n choose 3 p cubed. What do we need to evaluate for this bound? Well, we need to first define the dependent structure. So x alpha, x beta are dependent if and only if their triples share at least 1 edge. Of course, if they share 2 edges, they also share the 3rd edge. It's the same triangle. So the only non-trivial dependence you can have is that you have one triangle, another triangle sharing exactly 1 edge. And we saw that yesterday, the number of neighbors that each alpha has is 3n minus 3. We saw that was the D yesterday. That's the same here. And if no edge is shared, we have independence. So in this case, B3 is 0 because x alpha is independent of whatever is outside of this neighborhood of x alpha. So what is it we need to evaluate? B1, that's just plugging in. That's just n choose 3, 3n minus 3p to the power 6. That's straightforward, nothing to calculate, not much to do. The only thing we need to evaluate is x alpha times x beta for with beta sharing one edge with alpha. That means you have a total of 5 edges, right? And this is 1 if and only if all 5 edges are turned on, and that happens with probability p to the 5th power. And so we evaluate B2, that's the same here, except that we have p to the 5th power instead of p to the 6th power. I guess there should be a -1 somewhere. Let me think. No, I think this is correct, yes. I think there should be a +1 here, sorry. I think there should be 3n minus 3 plus 1, because here we include alpha itself, and here we exclude it. So there should be a +1 here. So what's the limit now? Or rather, I shouldn't say limit, I should say approximation. Limit here is the wrong word, it's an approximation, because lambda can diverge. You plug everything in, and what you get? You get a bound of order n to the 4th power and times p to the 5th power. And the bound is small whenever p is less than 1 over n to the 4/5. Again, if you put in p equals 1 over n or lambda over n, you'll get a limit, a Poisson limit, but p can be larger than lambda over constant over n, in which case lambda diverges, and yet you have a Poisson approximation within this regime. As you can see, there's an overlap in the regime between the Poisson regime and the Gaussian regime. There's an overlap. And that's very simple, because if you have a Poisson random variable with mean lambda and the lambda goes to infinity, that can be approximated by a Gaussian distribution. So it's not surprised that we have an overlap of the regimes where we can do both Poisson approximation and the Gaussian approximation. But of course, this approximation in some sense is much stronger because it's in total variation. So it's a very strong result that we have here. So the second approach, and that's probably, there's a famous book called Poisson Approximation, end of the 80s by Barber, Svante Jansson, and who was the third one? Holst, thank you. Where they mention this local approach in the first 10 pages, and the whole rest of the book essentially is using the size biasing approach. So how does that work? So here we're making use of the fact that the size bias -1 distributional transform is a fixed point equation for the Poisson. So if your W of interest satisfies a similar equation, not exactly, but close, you can use that to evaluate this quantity, okay? So, the quantity that we need to approximate. So let's see. First, let's define the size bias properly. So the size bias of W, we call that WS, is defined it's defined in this way. That's the actual point-wise definition. So the probability of WS equals K times the probability of W being K divided by, that's a normalizing constant. The size bias comes here from the fact that we multiply the probability of W being K by K. So larger values are preferred. That's why we bias towards larger values of W. And you can use this to prove that expectation of phi WS times expectation of W can be written as expectation W phi of W. So whenever you have W phi of W, you can replace that by the right-hand side. And you can go forth and back between size biasing and the W itself. Now, the important observation is this. How do you size bias an indicator random variable? What's the size bias of an indicator random variable? You can look that from here. The 0 always gets biased away. And for an indicator, all that's left is 1. So if you size bias an indicator, you're just forcing it to be 1. Okay, deterministic. So the size bias of an indicator is deterministic and equal to 1. Now, if you want to size bias a sum of indicators, fortunately, the construction is actually quite simple. Here's the construction. So you take W, it's a sum of indicators, they can be dependent. And again, Pi is the expectation of Xi, and lambda is the sum of these expectations. So here's what you need to do. you pick not uniformly, you pick one of these summons. We've seen this construction with the Gaussian case. Remember the exchangeable pair? You pick one of those, you replace it by something else, and there we picked uniformly. Here we have to pick proportional to the PI. Okay, so this is just a probability, and you pick your indicator proportional to its mean. Then what you do, what you essentially do is you size bias that indicator. That means you set it to 1. And then you have to adjust the other indicators to have the conditional distribution given that one you picked is 1. So you have to adjust the rest. So you construct a new family of random variables, excluding the one you've picked, and that has to have the law of the original ones, given now the one you've picked is 1. Okay? So that's these have a conditional distribution, given the one you've picked has been set to 1. Okay? And that's your size bias. That's a calculation. You can prove that this construction gives you the size bias distribution of W. The +1 here, so this is the sum over all the ones you've adjusted, and that's the one you've picked and set to 1. Okay, that's the +1 here. And then once you do that, you can prove a bound. You can prove that if W is integer valued, you can now upper bound the total variation distance by 1 over lambda, expectation W minus WS minus 1. Okay, so this here measures how well W satisfies this fixed point equation. If W itself is a Poisson random variable, right, the size bias is just the original variable plus 1. Then you subtract 1, you get back to the original. So that would just be 0. So if W is Poisson indeed, that's just 0. You can couple that perfectly, right? The construction of the size bias is just take the original Poisson and add 1. Then you've constructed the size bias. And then you subtract 1 again, you're back to the original. So this now quantity is a measure of strength of dependence, because if you pick one indicator, force it to be 1, how much you need to adjust the rest is a measure of how much of a dependence you have in your random variables. The more dependence you have, the weaker your approximation will be, and the less dependence you have, the better your approximation to the Poisson random variable will be.
What is dependence here? It's size bias.
It is a measure of, okay, W is a sum of indicators. We know if that these indicators are independent, we have a good approximation. Okay, that was this result here. This result, right? If they're independent, that's our best possible result for a Poisson approximation. Now, if there is dependence among these indicators, we have to measure that. Okay? And that's one way to measure that. It's using how well does it satisfy this fixed point equation, is to say that if I pick one at random of the indicators, force it to be 1, how much do I need to adjust the rest? If they're independent, I don't have to adjust the rest at all. Right? There's independence, so this will be very close. But if there is dependence, I have to do some adjustments. Yes?
WS is like some of indicators, like why is there a +1? Yeah, over there.
This one?
Yeah, the box.
Because this sum is excluding the J we picked. That's, I mean, you can write this down as a sum over everything, keeping in mind that the one you've picked has been set to 1.
And that's like a -1 in the next.
That's right, and then you subtract that. So it's how well can you couple the original one with the size biased one, excluding the one that you've picked. Is that more or less, does the answer a question? Measure of dependence is the small you can make, the better you can couple the two together, the less dependence you have in your W, the better your Poisson approximation will be.
I guess the point is, if you size bias a sum of indicators, you're essentially making one indicator 1.
Yes, 1 is forced to be 1, but you have to make adjustment in the rest because now it's conditional. Yeah. So let's see how this applies to isolated vertices in Adrian random graph. So W is the number of isolated vertices in an Adrian random graph. Isolated means it doesn't have any edges, okay? So it's isolated, degree 0. So let's write it down. Xi is the indicator. This should be a little I. Little I is isolated. And what's the probability that it's isolated? Well, it's the probability that none of the edges has turned on. Okay, so it's the probability that all the edges are off. That's 1 minus p to the power of n minus 1. So each edge, each potential edge adjacent to I has to be turned off. That's the probability. So lambda is just n times that. We can approximate that by n to the n times e to the minus np. Okay? That's the mean. And you can figure out how do we get, for example, a constant lambda. If n goes to infinity, how do you need to change p if n goes to infinity? That's the expression, p equals log n plus c over n. So it's essentially log n over n. That's how you need to choose p to give a lambda converging to a constant. So we have an actual limit in the number of isolated vertices. So here's the construction of the size bias and its coupling to W, okay? So we start with the graph and xi, again, sorry, this should be little I. That's the indicator that it's isolated. So now we pick j uniformly at random because all these xi have the same mean, so proportional to the pi's means just uniformly at random. So pick one of the vertices uniformly at random. Make that j an isolated vertex by erasing all incident edges. Okay? If there are any edges attached to j, remove those edges. And that's it. You have now a new graph, and your adjusted x's are just the indicator where the j is isolated in the modified graph. Okay? So all you do, you pick a vertex, kill all the edges adjacent to it, and that's it. You've constructed a random variable that has the size bias distribution. Okay, again, here a picture. This is the original graph. That's the j you've picked. You've killed these three, you have to kill these three edges. This vertex was isolated, it remains isolated. This vertex was not isolated, it remains non-isolated because it still has an edge here, but you've created a new isolated edge. By removing this edge, you've turned this 2 into an isolated vertex. So you have made some perturbation, right? You've changed the number of isolated vertices not just by forcing the one you've picked to be an isolated vertex, but others potentially also became isolated vertices. Namely, exactly the ones that are adjacent to you and have degree 1, those have been turned into isolated vertices. So what now is this difference? The xj you've picked in the original one is still there because it doesn't appear in this one. That's the -1, you remove it. So that appears in this difference. And then you have the sum over all after indicators minus before indicators. So this is whether it's an isolated vertex after you've done the modification. That's the indicator whether it was an isolated vertex before the modification. But this difference is easy to understand. This is 1 if and only if j was the one you've picked was the only neighbor of little j. That means if this little j has degree 1, only then do you see a difference here. If this was already an isolated vertex here, it remains an isolated vertex, so it's 1 minus 1. If the degree of j is bigger than 2, bigger or equal to 2, this one's 0, but you can remove at most 1 edge from j, so that remains 0 as well. So the only case is really if j, the neighbor of the one you've picked, has degree 1. So we can evaluate this expectation now. So that's the expectation of this. That's 1 minus p n to the -1 plus n minus 1. That's this sum times the probability that a vertex has degree 1, which is 1 minus p n to the -2, but one of them has to be turned on, which is probability p. Okay? And that's it. So that's our final bound. the total variation distance between the Poisson random variable and z is just upper bounded by this expression. And if you plug in p, this value, this choice where you get a limit lambda goes to e to the minus c, you can see that these both terms are order 1 over n, and you indeed have a bound of order 1 over n as a in a Poisson approximation. Okay, now I see I have 4 more minutes left and run out of slides. But in any case, if you want to reference the paper, I mentioned 2 moments suffice for Poisson approximation. That's the one I mentioned. And this book by Barbara Holst and Jansson. I don't know about okay, there must be some, anyway, Holst and Jansson on Poisson approximation, where the whole book is about constructing these size-bias couplings and prove approximation theorems that way. Okay, thank you very much.
Thank you, Adrian. Questions?
So, can you go to the X sub J slide?
X sub J.
X super J and the previous one. The previous. How do you define X sub J is, suppose the graph was not Adorshanian, the edges are not independent. Then.
Okay, assume the underlying graph is not heterogeneous. Then you have to modify the coupling. I mean, then you will have an influence in the sense that you pick your vertex, you kill all the edges around it, that remains the same. But now, if you have dependence between the edges, you may have to adjust other edges as well further downstream, because you now have the situation, given you have no edges there, it might influence other edges of not being there. So then this sort of cascades.
You must know your graph too.
You must know your graph. This, of course, this construction is only as simple as this because the edges are independent. Of course, it would also work if the P is not the same. You can have different edge probabilities. That construction is exactly the same and everything works very nicely. But if you have dependence, of course, for example, if you have a stochastic block model, there is dependence because the vertex labels, the vertices have labels, so that creates dependence between the edges. So that this construction would have to be done more carefully.
Then, I'm hogging the mic a little bit, but is this genre also valid for the convergence that Anita and Ellie's group are working on?
Say again?
The Anita and Ellie's group are working on this local weak convergence. So is this somewhat, can this sort of be phrased in that framework as well? Like you have a topology in which this...
So then you're asking about not Poisson approximation, but branching tree approximation, right?
Same idea, right?
Yes, yes.
Okay.
And no one's done that yet. It's something that might be of interest, like do Galton-Watson, Poisson, Galton-Watson branching tree approximation. So you approximate the whole tree, or at least a truncated version of it, and you get rates of convergence. But that's open, I don't know.
But it would still fit into this framework somehow. Yes. Of course, you have to work out the old...
Yes.
Yeah. Because as long as you're Poisson, everything is sort of nice. And if you're not Poisson, okay. Because yesterday you were also talking about some other distributions that you want to approximate that looked a bit more challenging. I guess if you do all your estimates, you'll find much more difficult expressions.
So the starting point to do Stein's method would be a characterizing operator. In this case, you would have to find a Markov process that has your tree as its station distribution, and that Markov process would add subtrees, remove subtrees, and hopefully not remove too much at each point in time, so you don't have big jumps in it. So you have like a little bit of a change here, and that would characterize your tree, and that's the starting point. Then you can use that to develop a theory on tree approximation. Yes, I don't think anyone's done that yet. I've thought about it a few years ago, but it was too complicated. I gave up.
Something to worry about.
Yes.
Okay, thank you, Adrian.
Thank you.